The Real-Time Mission Operations Center, and also this OVT, the Observatory Visualization Tool. And as we said, this is a simulation that shows you exactly what it looks like in space. So it's based on telemetry, but we consider this tool to be real-time. It's kind of worth mentioning that at the distance it takes signals to travel, it's about three light seconds away. So there's a tiny little delay, but of course that won't get in our way of covering this. So to begin with, I'm going to be joined now by Julie Van Kampen. And Julie is the Deputy Commissioning Lead, and she's going to be our expert guide today of much of what's happening that we watch unfolding. So, Julie, welcome. How are you doing today?
I'm doing great. Good morning to you.
So one of the things I think that's worth... Oh, please.
They're also doing well downstairs. They're getting ready to have us follow along with them.
Yeah, absolutely. So, the thing that we're going to be doing today is that pretty soon they're going to start unfolding this final wing of the mirror. And when that happens, we're going to be listening to real-time calls from the MOC, from the Mission Operations Center. So again, what you're looking at on your screen is you see the Mission Operations Center above Julie and myself, and then over to the left you see this wonderful simulation. And yesterday we had the deployment of the first of the side wings of the telescope, which happened extremely successfully. It was wonderful to be there. And today we're going to do the final wing of the primary mirror. So throughout the day, as calls come from the MOC, we're going to be pausing conversation. So please bear with us because we might be sort of mid-conversation, then we'll hear some sort of command that they're issuing from the mission control here, and we'll stop and make sure we know what's going on, and Julie will give us some guide to that. So please bear with us if that seems a little bit rough around the edges, but I think that's kind of the fun part about doing this live. So, Julie, I just sort of said it in general, but give us some more background. So what exactly is happening today that we're waiting for?
Sure. What they're currently working on right now is configuring the observatory, and specifically the deployment motor and the actuator motor, to make sure that they are checked out and ready to go before we start using them. So once those are checked out, then we'll fire the final pins that are holding it in its launch locked configuration with the mirrors off to the side, and then we'll use the deployment motor to move the mirror into position, and then use the actuator motor to lock it into that position.
Now, this is something that is happening at extremely cold temperatures. It was about, I forget exactly how many days now. We've all sort of lost track of time. I think I heard, Julie, I heard you saying that you've lost track of whether it's night or day. You've been sort of, in the command center this whole time. But we had the sun shield deployed, and those that 5-layer sun shield, each layer being about the size of a tennis court, it has been cooling the telescope down, blocking the sunlight. And I think one of the interesting challenges of these motors is that these motors are operating at such low temperatures. Is that correct, Julie?
Yeah. The motors are designed to operate at this temperature. However, what we do is have some heaters on them so we can warm them up to exactly the temperature we want them at for the deployments. Because it's for contingency, you also want to make sure that you could handle this no matter how long it took to take out the sun shield and get that tension. So the actual final temperature of these assemblies could be very different at this time, depending on how quickly or slowly those first steps of deployment went. So what we have is some heaters on these motors and some of the interfaces to make sure that they're at the exact temperature that we know that they can perform very well so that we have a very reliable operation today.
And just giving people a sense of what cold is. So I know one of the things that people can do is actually follow along on a website. That's Where is Web. You can actually see where it is on its journey out to the Lagrange point, L2, 1,000,000 miles away beyond the moon. And you can see where it is. There's also a measurement of temperature as to what the current temperature is, both on the warm side of the sun shield and then the cool side. So what's our approximate operating temperature today? You happen to know, Julie?
I didn't look specifically today at the overall telescope temperatures, but we were running down into the structural temperatures in the almost getting to 140 Kelvin, which I don't do the conversions in my head. I just work in Kelvin. But
Kelvin is what scientists use, and then for those of you out there that don't know that scale, it's the Celsius scale. Scientists use metric, and 0 is defined as absolute zero. So when Julie's talking about, she's talking about 140 degrees above absolute zero, so that's probably something well under 300 degrees or so, or maybe something around there. But yeah. Yeah. So are the temperatures 300? Yeah. Right now in the mock, are they checking on those motors, or what's going on right now?
Right now in the mock, yes, they are checking out those motors. They're in the middle of an aliveness test, and then what they do is they make sure that the motor is right in the position that they want to start in.
Right. One thing that I was rather surprised at yesterday during the deployment of the first wing was just how quickly that goes. So today what we're going to see, hopefully, when they give the command, is a relatively quick movement of the mirrors. It was about 4 minutes or so that it took to actually swing that wing around. And then after that comes a long series of locking it into place. And as we lock the mirror into place,
Muito bom dia a todos, meu nome é Robson Rodrigues, sou repórter, editor e apresentador aqui do canal Olhar Sideral. Bom sábado para todo mundo, onde quer que você esteja, no carro, no trabalho, em casa, enfim, em qualquer lugar, estando nos assistindo. Muito obrigado pela sua audiência. Tenham todos, como eu disse, um excelente final de semana. Estamos acompanhando aí a cobertura da abertura do segundo lado bombordo do espelho primário do James Webb. Estamos assistindo aí a transmissão ao vivo da NASA e a gente vai acompanhando e comentando aqui com vocês na medida do possível. Nosso agradecimento todo especial à Itanet, a maior e a melhor rede de fibra ótica da região, atendendo não só a região do Espírito Santo, sul do Espírito Santo, como norte, noroeste fluminense, região dos lagos e também agora chegando ao Grande Rio. Acesse www.itanet.com.br e confira a infinidade de combos e facilidades e recursos que a Itanet tem a lhe oferecer. A Itanet não só é a melhor e a maior rede de fibra ótica da região, mas também fomenta o esporte, o lazer, a cultura e o entretenimento. Acesse www.itanet.com.br e confira. Nosso agradecimento também especial à Inusitec, inovando com tecnologia.
So much instrumentation all over the telescope, whether it's motor telemetry, thermal telemetry, whether it's indications that the entire spacecraft has.
Bom, para você que não é inscrito no canal, se gosta de assuntos relacionados à astronomia, astronáutica, ciência e tecnologia, se inscreva no canal, não deixe de marcar o sininho. Isso lhe ajuda a ser notificado pelo YouTube sempre que tivermos um conteúdo novo no canal.
To handle all of the steps and going back and forth with our operational control center, our flight control room, our OC in the front room. And if you
Ainda hoje aqui no canal Olhar Sideral iremos também acompanhar o lançamento do foguete sonda em mais uma missão da NASA para o estudo dos efeitos do raio-x baixo na atmosfera da Terra e também nos satélites em volta do nosso planeta.
They'll talk about what is into the command line, and that means what has been put onto the workstation in front of them. And before the command is sent up to the observatory,
continue com a gente, deixe o seu like, compartilhe com os amigos, isso ajuda na divulgação do canal. Mais uma vez, muito obrigado a todos. Daqui a pouquinho retornamos com mais informações.
You'll hear a lot of times that the script will confirm that it's been received, and then the next step will be to hit go. It's like a lot of times on Windows, it will say, do you really want to do this? So you have to say yes twice.
And I understand we're about 4 minutes from getting the command start release to fire, as they say. So that will be happening pretty soon. Another one of the people that you often hear called out is sometimes it's a little bit funny to hear is mom. You'll say somebody referred to as mom. And tell us a bit of who that is, Julie.
That's the mission operations manager, and you'll hear him from time to time come on and do a poll of all of the various subsystems that are supporting today, like the spacecraft and the instruments team, so that everyone's ready to go on with a major step as we go through our deployments today. So he's the overall lead of both the front and the back rooms. So the back room is our spacecraft and our subsystems that support that. We also have a second back room, which we call the SI room, which has our instrument team in it.
I think that person on screen that I see now is Bill Oakes. He has been.
That's Bill Oakes.
Yeah, exactly. That's right. So tell us a bit about Bill Oakes' role in this mission.
He's the program manager for Jwst, and he's over the whole program, both the operations side, the development side. Everybody eventually works for Bill as you go up our chain, so he's been great, and he probably doesn't even know that he's currently on camera.
So one of the things that people were asking before is how are we actually getting this information down from the spacecraft? So you mentioned that there's telemetry. There are detectors all over the spacecraft measuring things like electrical current or temperature or all of these things. But how is that data actually getting to us here at the Space Telescope Science Institute?
Oh, that's an interesting point. So we have antennas on our observatory, and if people have watched along, one of our very early deployments was one of our antennas, and from that, signal is transmitted down to the Deep Space Network. So this is the same network that we communicate with, let's say, the Mars rover on. There's one in Canberra, there's one in Madrid, there's one in Goldstone, and these very large dishes then take that signal, convert it into something that can be sent on a ground network, and it's sent by ground network to here, where we are both the Space Telescope Science Institute, and the once it comes into the Institute, it goes through a whole series of processing, and then it comes up to our screens and monitors in a way that we can interpret That was the last set of commands sent to get the motors ready to verify that the motors are ready before we go ahead and do the launch lock release. In the top view, we have our deputy program manager, John Durning. Not sure what his sign says. It says commissioning manager, but he's the deputy project manager. He works directly with Bill Oakes.
I believe we're about 2 minutes now away from firing. For those of you who may have just joined us, you're watching at live coverage of the unfolding of the primary mirror for the James Webb Space Telescope. Yesterday, they successfully unfolded one of the wings. I believe that was the port, the left side wing. And today we are doing the final wing, which will hopefully by the end of the day leave the primary mirror completely extended and unfolded. So we're only a few minutes away from that command to start first slowly and then a little bit more quickly unfolding that wing of the telescope. And you can see the configuration the telescope is in on the left side of your screen. This is a computer image, but it's based on actual real-time data from the observatory. So this is what Webb would look like if you were out there to see it. Of course, it would also look a lot darker because the sun shield now is completely blocking light from the sun and any sort of heat from the Earth and the Moon. And the telescope is operating very dark and very cold as it was designed to do. So we're very close. I believe the calls will be coming shortly, so we'll probably take a pause in conversation now and begin listening to the calls. And Julie, as we have time in the conversation and the calls come, please step in to tell us what those commands mean and be our interpreter so that we know how this process is going.
Sure.
I have to say it's tremendously exciting for me. I have been looking forward to this quite literally for decades. This is something that has been a part of my family, have worked on this. So this is a very proud and very exciting moment for me. It's been an incredible couple of weeks. Julie, how are you feeling? I know yesterday we ended up smiling a lot as we saw that wing move into place. Big smiles. I know that one of the things that was tremendously important to the unfolding of this telescope. Let's just listen.
Here we go.
I have confirmation from Dep Lead that they agreed that all of the sync moves look good. We're ready to command the launch lock releases. You're ready to go with 693.029. All channels safe verified. The command line looks good. You're go to execute.
Copy that. If you have to go to execute.
You're go to continue.
Copy that to continue.
And at this point, they're going to send the command, which puts a current through a fuse wire and releases the launch locks that are holding the side of the mirrors back against the structure of the back plane of the mirror. And that was done so that we fit inside our fairing of our telescope. We're all folded up like origami. Obviously, the sun shield has been deployed, and you can see how big that is relative to the mirror itself right now. So the last of this is to bring out the mirrors, and then we'll have our telescope mirror fully deployed.
And that's what makes this such a historic moment, is that this is the first time we've unfolded such a large space observatory. And first came the sun shield. Then there was the secondary mirror, the focusing mirror that had to come out in front of the telescope to focus the light. And then yesterday, the first of the primary mirror side segments, the wings. And then today, the second one of that. This will not be the end today of commissioning the telescope. There's still more to come. One of the major things that needs to happen next is the focusing of the mirror. The mirror has 18 segments that all work independently and can all be adjusted independently. We'll talk more about that after we unfold the wing segment. We'll have some time to talk with some guests to talk about that. But that's the incredible thing, is that this large observatory was folded up to fit inside the rocket, the Ariane 5 rocket, launched from Kourou, French Guiana, in South America. And now we are unfolding this observatory. And this is the first time this particular procedure has been done in space. And this is just wonderful to watch. So you were mentioning that you send a current through these. Is this an example of the actuators that we've been talking about before? That there are actuators that have to release, or this is something a little bit different?
No, this is the same. These are like a pin that's held in a like a cup cone assembly, and when the fuse wire breaks, it loosens up or wire that's tightly wound around it, allowing the pin and the cup to separate. All that, all those little components are captured into the mechanism itself. So none of it's free floating in space as debris, but it allows those two pieces to move apart. And there's going to be 4 that actually fire together. They're just about ready to continue. Here. She says go to execute.
Copy. Go ahead and execute. Execute.
And your go to enable.
Copy. Go to enable. There we go.
And what they'll see now in their telemetry is they might see a disturbance on the entire observatory of these launch blocks actually coming apart. The entire observatory might just as like when you unlock your vehicle, you can hear the click of the door unlock. There's almost like a little vibe in the whole structure that comes through that we can. Sometimes we can pick up in other telemetry.
And I see I can enable your go to arm.
That these fully release.
Copy. Go.
In fact, I know the design of these actuators was specifically done so that they don't jar the telescope very much. They're actually very gentle.
Yes.
But even just that little bit of vibration can be
I see I
detected.
confirm armed. We're waiting on the stored command sequence.
And the stored command sequence is we don't ever want to break a command between the time we tell it to fire and
and all stations. Our next go will fire ordnance OTE LRM Group 7. OC, your go to fire.
Copy. Go to fire. See, you have to go to fire.
hear the music.
I believe the music you're hearing, that's real. That's in the control room. They're
Yeah, that's in the control room. I actually hear it twice because I have my earphone on and then I hear it through here. So I had a hard time figuring out if you could really hear it, if it was just me for a second.
yeah, right. Obviously an air of excitement, and certainly, everybody is a little bit, their nerves are, on edge, but lots of optimism, lots of excitement, and lots of smiles. So that's it's an emotional moment for all of us.
Everyone's been working on this since the day of launch. Our launch deployments started with our very first one that was caught by the rocket itself as it floated. Jwst floated away from it, the upper stage, and it's been nonstop, day after day since then. Having each deployment come along in series, everyone has gone very well.
I see this is step off. I can confirm safe and disabled, and we're ready to continue with 693.031.
Okay.
This is the step to actually do
Okay,
the
the
firing.
command line looks good. This is for OTE LRM Group 8, and you are going to execute.
Copy. You have to go to execute. Execute.
And you're going to continue.
Copy. Go to continue. You have to go.
There's a total of 4 mechanisms that do the launch lock. 2 are at the hinge where which is actually closest to us in the display, at the joints, 1 at the top, 1 at the bottom, and then 2 kind of hold the wing back to keep it from rattling during launch, and are at the far corners
See, I
of
can
the
confirm
side
and
mirrors.
you're going to arm.
Copy. Go. You have to go to arm.
I can confirm armed, waiting for the stored command sequence enable.
The thing that's so amazing to me is that what's happening today is the end of 178 release mechanisms. You know, every single one had to work.
Yeah, all stations are next go. We'll fire OTE LRM Group 8. OC, you are go to fire.
Roger. Succeed. You have to go to fire. Copy that.
Yeah, there was a lot of work to put into these. A lot of people have heard about our single point failures. Each one of these itself was a single point failure. In other words, if one of those 4 launch releases does not release it, we're not able to move this side of the mirror forward into position. So this would be our last of these 4 single point failures. There's still other single point failures and some that stay with us for the life of the mission. Different areas of structure or a mechanism. If the mechanism fails, we don't have a second path of light to bring the light down. But these are major milestones in getting the observatory into its final configuration.
For those of you who are joining us, you're looking at live coverage of the commissioning of the James Webb Space Telescope. Today we are unfolding the second of the wings of the primary mirrors. Joining me is Julie Van Kampen. She is the Deputy Commissioning Engineer. You can see people there excited and happy.
Mom copies. Thanks, Step Lead. Glad to have the plot so we can follow along. Share your enthusiasm. That's awesome. 178 out of 178. Congratulations. Thanks.
They just fired.
It confirms that all of those mechanisms fired, 178 of them.
Over
the course of the
hear
last
on the
I see this is step ops on ops. I see that rock has completed. We're ready to continue with 693.032 DEU to standby.
Copy that.
And they could see indications in
And the
telemetry
command line looks good. You're good to execute.
Copy. You see,
that
you have to
everything
go
is
to
successful.
execute.
And you're good to continue.
Copy. And you have to go to continue.
The next couple steps are going to be getting the deployment motors ready again. So before they checked them out, they had to put them into a standby mode while they were doing the firing. That was the safe configuration that you heard the deployment lead speak to. Now they're going to get them back into the configuration, and then they'll get ready to do their first small move.
OC, I can confirm we're in standby round robin. We're ready for 693.033 to restore default torque limits. The command line looks good. You're go to execute.
Copy. You see, you have to go to execute. Executing.
And you're go to continue.
Copy. Go to continue.
And earlier we had mentioned the position called Mom. That's the Mission Operations Manager. And the elbow we're seeing in the top screen, that's Carl Starr. He's the Mom of JWST. When they do the small mirror move, the small motor move on the mirror here, in our tool that we get to see on the screen, the OVT, the Observatory Visualization Tool, we don't actually, it's such a small move, we won't see the tool actually change at all. It won't be until the major move before we can actually see it on this tool. And it looks like they're calculating that's going to be another 20 or more minutes until we actually see the full move take place.
Right. We're sitting here now. We're actually watching the Mission Operation Manager, and you'll also be seeing live coverage from the MOC, the Mission Operations Center at the Space Telescope Science Institute in Baltimore, Maryland. I'm there as well, although in an isolated conference room, so I can speak to you unmasked. Of course, we're operating under COVID protocols, which has made a challenge, but it's a happy and festive day here, and we're really looking forward to this next deployment. Later on in the program, we'll have a chance to take some of your questions from social media, and today we're asking you to use the hashtag #UnfoldTheUniverse. So hashtag #UnfoldTheUniverse. We'll be stopping our commentary with your commands. So, we may have a conversation, but then we'll stop to hear how the commands are progressing. As first, they make a very small movement to make sure the wing is moving correctly and all the motors are functioning correctly. And then in about 20 minutes from now, you will see on the left-hand side of your screen, you will actually see the wing click into place. And then after that, there will be a couple hours of latching it, of making sure that this is fully in its extended, permanent configuration. I see Julie's got a big smile on her face, which I love to see, because it's a lot of work.
So,
up at the top there,
again,
Bill Oakes. Yeah.
Yeah.
Bill Oakes is the program manager, and you'll see him throughout this. As Julie said, he's sort of the head of the mission. Everybody kind of reports to him at this point. There's an interesting teamwork between scientists and engineers on a mission like this. And actually, Julie and I were talking about this earlier, that, I come from the background of being an astrophysicist. And when I think about Webb, I mainly think of all of the incredible data and the questions. The scientific questions. I'm looking forward to being able to explore with the telescope. Julie has a very different perspective. Julie, tell us a bit about your position as the deputy commissioning engineer. Tell us about what that job entails.
Sure. As the deputy commissioning engineer, I've worked to try to make sure all of the various pieces that it takes to commission the telescope come together in a way that makes an engineering sense. So there's a lot of people who have worked for many years to make sure that it comes together. So you kind of learn to be the Jill of all trades. And from that, I moved to NASA and got into the testing department and was able to do actually a lot of the Hubble servicing missions from the testing side to get those instruments and components that were being sent to Hubble on the different servicing missions ready for those missions. Then eventually I moved over to JWST, and I've been on JWST since 2003. And I've been a systems engineer on the instruments, and then the payload, and now onto the commissioning.
Wonderful. So we will pause our commentary when we hear commands from the Mission Operations Center, but we do have time to take a few questions on social media. So whenever people ask questions like this, I'm
about the Webb telescope is with these independent mirrors. We can handle so many different scenarios like that. For instance, if one of the mirrors, either, let's say a piece of debris hits it, or during its launch and ascent phase, some of the stresses were higher than predicted, and we had a problem that broke a mirror or an actuator behind the mirror, we could actually take that mirror essentially out of the image by making it very much out of focus with the rest of the telescope. And you know, if anyone's ever experienced having a floater in their eye, or something like a scratch on
cameras of the telescope. I remember at the Goddard Space Flight Center when they replaced some of the cameras on the Hubble Space Telescope. They brought some of the old cameras back for
And
analysis.
DevOps can confirm operation frame 6. And we're ready to continue with the small motor move. So we're ready to go at 693.039.
Copy, just on the window.
That command line looks good. You're go to execute.
Copy that. You see you have to go to execute. Executing.
And you're go to continue.
Copy, go to continue. You see you have to go to continue. Copy that.
And stand by while we review parameters.
Copy that. Standing by.
So we were talking about the debris. Also, being at L2 is very
I see
useful.
the parameters look good. You're good to move the motor.
Copy that. You see you have to go to move. Copy that. And pro complete.
DevOps copies, and you can queue up the stop.
Copy that.
And the motor status is moving.
Copy, copy.
Seeing at Goddard, I remember the cameras being brought back for analysis. They were analyzing every tiny little crater that was made by a little
Olá a
piece of
todos
dust,
mais
a
uma
little piece
vez.
of debris.
Tivemos aí pequeno
But you said that
delay na
L2,
nossa
for example,
transmissão
is
devido
actually a
aí
very
a
nice place to
nossa
be. It's
máquina
actually
está
kind of a cleaner place when it comes to space jumps. Is that correct?
debilitada, mas estamos aí
Yes.
fazendo o melhor que podemos para
Low Earth
oferecer a
orbit
você
Hubble is in it.
informação e qualidade
Has a
na
lot of
nossa,
space debris.
na nossa
As everybody has
transmissão.
seen,
Para quem não me conhece, meu nome é
And I see
Robson
you are
Rodrigues, sou
going to
repórter,
execute
editor e
soft
apresentador aqui do canal Olhar Sideral.
Copy that.
Espero que você
You have to
esteja
go to
gostando
execute.
aí do nosso conteúdo. Nós estamos aí acompanhando junto com
And you're
vocês
good to continue.
o desdobramento da segunda parte do espelho primário
stopping the motor move
do
now.
telescópio James Webb. E a equipe de operações da missão Webb deu o sinal verde para avançar a extensão do seu painel de espelho primário de este bordo. Inclusive, mais cedo eu falei bordo, desculpa, me equivoquei. Na verdade, é este bordo. Esta é a última das principais implantações no observatório e a sua conclusão definirá o cenário para os 5 meses e meio restantes de comissionamento, que consiste em estabelecer uma temperatura de operação estável e alinhar os espelhos e calibrar os instrumentos científicos, que ficam na parte posterior, na parte de trás aqui do espelho. Como podemos observar aí nessa imagem, estamos aí acompanhando junto com vocês a astrônoma da NASA e também manager da NASA também, apresentadora também, e uma cientista ao lado dela, uma pessoa que trabalha no setor da ESA, que está aí monitorando e acompanhando aí o desdobramento. Parece que o processo já iniciou e aí a gente pode acompanhar também aqui embaixo, nessa parte aqui de baixo, né, o track do James Webb Space Telescope. A posição em que ele está, a localização, né, a distância, a velocidade, o lado quente, o lado frio. Aí já está caminhando para o seu 14º dia. Ontem teve a conclusão da abertura do primeiro lado, né, do lado de bombordo do espelho primário, e hoje está sendo concluído Está sendo iniciado, né, a conclusão da abertura final do espelho primário do James Webb. Bom, se você está gostando, deixe então seu like, compartilhe com os amigos, comente, interaja junto com a gente. É um prazer e uma honra a sua presença. Para você que não está assistindo agora, mas vai assistir depois, muito obrigado pela sua audiência. O agradecimento também especial ao apoio cultural da internet, a maior e a melhor rede de fibra ótica da região, atendendo a região do sul do Espírito Santo, norte e noroeste fluminense, região dos lagos, Grande Rio, e agora chegando também a regiões próximo ao sul de Minas Gerais. Acesse www.internet.com.br e confira os combos e as facilidades que a internet tem de oferecer. A internet não é só um provedor de internet, mas um provedor também de cultura, esporte, lazer e entretenimento. Visite a página da internet nas redes sociais. Então vamos continuar acompanhando junto com vocês e daqui a pouquinho a gente volta com mais informação. Lembrando que hoje tem também lançamento pela Wall Up no site da NASA e nós aqui do canal Olhar Sideral vamos estar acompanhando junto com vocês. Meu nome é Robson Rodrigues, sou repórter, editor e apresentador do canal Olhar Sideral. Seja bem-vindo e fique à vontade assistindo junto com a gente. Daqui a pouquinho a gente volta.
And we have some time as they latch telescope, a couple of hours into its final configuration. So we'll have different guests and experts to talk about what's going on when that happens. I'm joined by Julie Van Kampen, and she is the Deputy Observatory Commissioning Engineer.
RTCP is complete.
DevOps copies. It looks like that load completed successfully. We're ready to continue with 693.043 DEU to operate for in6.
Copy that. On the window.
And the command line looks good. You're go to execute.
Roger that. Go ahead and execute. Executing.
So they've just put the
And you're
mirror
going to
back.
continue.
Right.
Copy that to continue.
The deployment motor back into its operational state. It was taken out of operational state to do a reconfiguration. And now it's ready to do the full move once this is done.
We're coming to you live from the Space Telescope Science Institute in Baltimore, Maryland. This is happening in real time. The James Webb Space Telescope commissioning, the final wing of the primary mirror. You're looking at live coverage from the Mission Operations Center, the MOC. Command to deploy the wing is imminent. We're waiting for it any minute now. And then we will watch on the observatory visualization tool. See that it'll just be a couple of minutes, something like 4 to 5 minutes, and then after that we will come back with more commentary about the observatory, and we'll talk to some of the people that are some of the science leads as well about some of the scientific questions this observatory has been designed to answer.
They've just given the
Stand by
command
while we
to
review the
go ahead.
parameters.
Stay standing by.
They're reviewing the parameters to move
Okay,
the
I
mirrors.
see those parameters look good. You are good to move the motor.
Copy go to move. This you have. Copy go.
And this will move the mirrors into their final position.
Copy.
The screen to the right shows us our ground station.
And the motor status is moving.
You can see the mirrors move in the visualization tool. It'll take about 4 minutes. And then we'll do it.
reminder, this is real live footage. There's a 3-second time delay. It takes that long for light to travel at 186,000 miles per second. The James Webb Space Telescope is now well over 600,000 miles away. I think you remember about this.
Go ahead.
I was just going to say, remember that this visualization is real. This is not pre-recorded. It's based on actual data coming to us from the telescope, being downloaded right now.
And the important thing about the light delay is not that the light takes that long, but the data, which moves at the speed of light, takes that long to come to us. I know that was a question we had on some of our social media before.
With the status, we have started our deployment into the deployed hard stops, and our current looks really good, nice and low.
Mount copy.
That was another of our deployment engineers confirming that everything looks good with our mission operations manager.
It's exciting to actually see it moving. You know, there it is on the visualization tool. It's getting closer and closer.
Yep, it's going to be momentous when it finally comes into position.
The first wing was successfully deployed yesterday, and now this is the final part, the primary mirror being put in place. Julie, give us a sense of the scale. These mirror segments. I mean, I had the honor of watching this being built. A lot of it at Goddard. How big across, for example, is one of those hexagons?
They're about 1.5 meters across from tip to tip. The hexagons are quite large. It's amazing to actually be in the clean room and look up to see the whole mirror assembled, towering above you. There's no amount of seeing it on photos that kind of gives you the sense of actually standing next to it in our clean room when it was assembled. And, as we talked about before, and once it's fully into position here, the final shape that our primary mirror is going to be called a tricontagon. It's about a polygon.
The step lead on ops are about 3/4 of the way through the deployment, and everything still looks really good.
Vamos aí então já quase a conclusão da abertura do lado este bordo do espelho primário do James Webb. Estamos aí em tempo real, daí os dados, né, de telemetria da NASA. A gente acompanha o momento de conclusão da abertura do estágio final do espelho primário.
From keeping any of the backside of the telescope warm. There's one on each side that comes down passively as the motor moves this forward. And then the gaps between the mirrors
quase concluído.
Are very small. I think it's on the order of several millimeters.
Ok. Muito bem, parabéns à NASA, à ESA e a todas as equipes aí das agências espaciais envolvidas nesse grande projeto. Mais uma fase concluída. Muito legal isso. Esse que é, sem dúvida, o telescópio, maior telescópio, né, o mais poderoso até hoje desenvolvido, né, pela mão humana. O mais complexo telescópio de ciência espacial já construído é o James Webb. Está aí com o seu espelho primário completo, ainda em fase de travamento das partes, né, do espelho.
think you
Isso
can hear
aí.
the relief in our deployment ops
Parabéns à
And you are
NASA,
going
à
to
ESA,
activate.
à CSA
Copy, go to name.
voice.
e a todos envolvidos aí por esse grande projeto.
I have to say, I just feel this kind of glow, in my
James
chest
Webb
right now,
olhará
seeing
para
that mirror all
mundos distantes ao
deployed all
redor
together.
de outras estrelas e investigará
The
as
size of the
misteriosas
mirror
estruturas
allows us
e
to collect,
origens do nosso
more light
universo
from fainter
e o
objects.
nosso lugar nele.
A lot of cases that means farther away
O Webb é um
objects
programa
that light
internacional
many
liderado
billions
pela
of years
NASA,
travel to us.
com seus
Chances
parceiros que é a
universe
ESA, a
as it
Agência
was,
Espacial
perhaps,
Europeia,
only a couple
a
hundred million years
Agência
after the
Espacial
start of the Big Bang.
Canadense também.
The sensitivity of this mirror will
Bom,
allow
nós vamos
that.
continuar acompanhando, porque
And,
ainda
the size of the mirror
logo
also
depois
gives us
dessa
a
live
clearer, higher
terá também
resolution,
uma
able to see
coletiva
more
de
detail
imprensa,
in space than ever before.
qual participará
So
com
this was
certeza
something that absolutely had to
personalidades
happen.
importantes
We
da
had to-
área
had to unfold this mirror, the secondary
da
focusing
administração
mirror,
da
and
NASA,
come
da
out.
ESA,
And,
também
and
da
then, a
Agência
little bit more than
Espacial
a week ago,
Europeia,
the amazing
a
sun shield. And there it is in front
CSA.
of us. You're looking at this animation. This is not
Ok.
a pre-made animation. This is based on actual
Continuamos então
data coming from the
aguardando
telescope to us
e
right now.
vamos
We are,
nessa.
live at the
Mais uma
Space
vez,
Telescope
obrigado aí por
Science
você estar nos
Institute.
assistindo,
And,
mesmo
we have
depois.
successfully
Obrigado,
unfolded
deixe o seu like,
the last part
compartilhe
of the
com os amigos se
primary
você
mirror.
gostar, isso ajuda
After
na
this,
divulgação
there
do nosso
are still
canal.
more commissioning acts
Muito obrigado
to come,
pelo
very
apoio de
important
todos
ones. For,
e vamos
example,
continuar
focus
acompanhando.
Okay, desktop
mirrors
can
meet up
confirm that 256 is active in the delayed state. And I've confirmed with the depth lead, they're ready to begin the 3-door latch off stow and latch to safe. So we're ready to continue with 693.048, move 1 of 20.
Copy that. On the window.
And that proc looks good. You are good to execute.
Copy. Is you happy to go to execute? Executing.
You just heard
And
our
you're good to
deployment
continue.
lead
Copy, go to continue.
go through a mouthful of description there of what happens next. There's a hook latch, and it's basically really that. It looks like a big latch, like you would hook possibly on a bathroom door or a tie down. If you had tie down straps to hold some packaging onto the back of a vehicle, it's actually a hook. And you heard her call it 3-door, and what that means is it's essentially it has a couple of different degrees of motion that it can do.
Stand by for perimeter review.
Copy that. Standing by.
Each of the latches are a little different in which degrees of freedom that they can move in, and so the 3-door
And
is
OC, the parameters look good. You're going to continue with the motor move.
Copy, go. You see you have to go to continue.
is one of the types that we have.
This latching procedure will take a couple of hours. We will be here through the entirety of it. We will be able to tell you when it is complete. And we may pause our commentary now and again, but we'll have different guests talking about aspects of the engineering and science of the James Webb Space Telescope through the next few hours. And this procedure will take quite a while. Can you tell us a little bit more about the latching, what we're going to be witnessing in the next few hours, Julie?
Sure. There's actually several latches. The next one that you'll hear her talk about will be one of the 2 doors, and there's 4 in total, I believe, and each of these will come into position, and then they'll very slowly. They want to make sure that they don't do something that's called like over-constrained. And as anyone who understands how a mechanism might move, you can easily kind of get yourself jammed into a position if you try to tighten one thing before you're completely aligned with another. Almost like when you change your tire, you want to kind of do that star pattern to wiggle it into just the right position to make sure it's flat. You don't want to tighten one of those bolts before you get the others snug, and you want to tighten them up in a pattern. So they'll do the same thing with these latches. They'll make sure that they're done in a very precise order, that the different degrees of freedoms of each of the latches are coming into play in the order that they had planned, to make sure that they get that mirror latched in and locked down in the absolute best position so that those mirrors are in range for what they need to do for actually defining the surface of that mirror with the actuators and motions that will come next in the next couple weeks.
Well, Julie, thank you so much for being with us for this procedure. We're going to come back to you later on as this happens. At the moment, we are going to have one of our expert guests come up. We're going to be joined by
that motor move looks good. We are ready to continue with 693.049. 3-door latch to safe, move 2 of 20. And the command
Thank you for
line
having me.
You're good to execute.
Copy that. Go ahead and execute.
Thank you for having me.
And you're good to continue.
We'll come back to you later.
So you have this one.
Absolutely. The next person we're going to be talking to is the Associate Administrator for Science at NASA, Dr. Thomas Zurbuchen. Thomas, it is wonderful to see you. How are you feeling? To tell me about what you just observed.
Oh, I'm emotional about it. What an amazing milestone. We see that beautiful pattern out there in the sky now, almost complete. Of course, it needs to latch, but what an amazing milestone. Just ahead of it, 178 out of 178 of these actuators that had to fire the right way. I'm just so amazed and in awe about this team.
So one of the things that I'm just sort of, I haven't seen you for a while without a mask. They have us all in isolated rooms, and you're always clean shaven. You look a little bit different today. Is there is there some story behind that?
You notice, right? So, basically what happened is after we launched, frankly, I told my wife, I'm not going to shave until this entire telescope is fully deployed. This is like my favorite sports team. When they're in the playoffs, right? You have to be sure that you fully support them. So that's what I'm doing here. I can't wait to shave. Michelle, my wife says, are they done soon?
And so that actually gives us a chance to talk a bit about what's coming out next. So, about how long do you think it's going to be until you shave?
Well, I fully expect, assuming that everything goes well today, I fully expect to shave today. And I just want you to know, this team is basically on track within a half a day or so of the fastest schedule that we had outlined. Frankly, I sat there today with some of the managers and said, if you ask somebody, 2 months ago, even a month ago, hey, we're going to be done on the 8th of January, what would we have said? I said it's massively optimistic, frankly, unrealistic to assume that. I think this team is just incredible. Back to my sports analogy, we're seeing that the team on the playing field, and it's just an awesome team, and frankly, over and above all expectations that anybody might have had.
When you're talking about the team, it all coming together, but then there are also some tremendous challenges that this team has faced. And I know that that's something that you've been there with the team for quite a while now. Can you give us a sense about? We not only did we have COVID, where we were all trying to do this and be isolated and be careful for each other's safety and all that, but there were all kinds of other challenges. Tell us about some of the things that in your years on this mission, you were like, wow, I'm amazed they overcame that.
Look, I just want to tell you first, Michelle, I'm very humbled to be part of this team right now, and I know so many others were part of this team for decades before I even showed up. I've only been part of this team for 5 years, and I'm honored to be part of the team. Yes, we've had a number of challenges. If you, of course, look at everything that go backwards, anything with the deployments. Some of the challenges, frankly, that the team immediately addressed, they made it look easy, even though some of these challenges, frankly, were tough. You go back in time, and of course, it's very hard to think about the grit of this team that we're seeing without thinking of COVID, right? I mean, what's really amazing is how they overcame that, right? How they did not, they took every excuse they could to stay on track, right? It's so often, Michelle, sometimes we see teams, in our private lives or even, elsewhere, where all of a sudden, people take excuses to not fulfill goals. This team found every excuse to do so. You go back in time and you realize, how hard it is to be truly a single team. And Michelle, it's not just the engineers, it's the good people on Capitol Hill who are allocating the budgets, the people in the White House, all the stakeholders there. And I think what Greg Robinson, and for me, it's just really important to say that name. What he managed to do and kind of overcame is really building a team from the top all the way to the technician, the single team. And of course, that's why it's going so well. All right, because of unified teams, are a beautiful thing to watch.
This is the depth lead on ops with the status. We're a couple minutes into our move to the safe position on the 3-door latch. Everything looks really good. Strains are low, and the strain offset came in right where we wanted it. So we're looking good.
Mom copies. That's Austin, depth lead. Keep going.
So as the Associate Administrator for Science at NASA, you are a scientist, and there's some incredible scientific goals with this mission. And like we said, that this all started from questions. We launched the Hubble Space Telescope. We understood there was so many more things to see, even farther back in time. Give me a sense about some of the science that you're most looking forward to. Hopefully, that this mission will accomplish.
How much time do you have, Michelle? Right, I'm going to give you like a couple. But I've been doing a lot of reading and thinking about this kind of early universe and the galaxies, and for me, the potential impact of primordial black holes in this whole discussion, really the relationship of galaxies and black holes that are so tight. As we look at today's galaxies, kind of in our neighborhood, like how did that go there? For me, it just boggles my mind, to think of these enormous structures in the universe that are in the past. I'm going to give you a second example. Michelle, and of course, it's about finding life elsewhere, but I'm going to focus on our own solar system. We're going to make observations, for example, of Europa. We did that with Hubble. And there's amazing papers out there from in Nature and Science that says just marginally we can see kind of emissions of Europa that kind of are similar to Enceladus, for example, where water from these subsurface oceans is coming out together with organics at Enceladus. The question is, does that happen with Europa? And of course, we're moving towards a launch of Clipper in 2024, and we want to make sure that if there are such emission points, that we know that, because we want to take the measurements with that amazing mass spectrometer on Clipper. There's similar type of discussions on Mars, where of course we're in the middle of another huge adventure, trying to get these samples back in the first round trip to another planet. And for me, again, observations of the Martian atmosphere, its composition and its dust components are just so critical.
this is something that I think that, I really enjoyed seeing your leadership on in the last years is no mission stands alone. We have missions that each one supports the other. It's not just this mission, then that one. There's a strategy that everything works together. So like you said, for exploring the solar system, you have something like the Webb telescope, which from a distance can see things like Mars, Europa, places like Titan. But then we have missions that are poised to go there and explore closer up as well.
Oh, I strongly believe that, right? What's so beautiful about nature and so amazing about the science program we have at NASA is the interconnectedness between the different questions that are there. And to me, that has always been one of the most exciting parts of studying nature, is to see relationships that were not innately recognized there. And I think the more we learn about nature, and especially in astrophysics, the more we see some of these connections, right? I'm always in awe. I read some papers, not as many as I would like to, Michelle, but nonetheless, I read some of the papers. I realize that atmospheric models of exoplanets so often are done by our good people in Earth science, because they know how to do
we are halfway through our
in ways that nobody else can. So yes, they belong together, all these missions, because nature is also
haven't changed significantly.
Absolutely. Listening to commands from the mock, making sure we stay up to date on them. But absolutely. I mean, you mentioned the first stars, and there's probably plenty of people in the audience that don't really know your background as a scientist. I mean, maybe you could a little sense about your scientific expertise and how you came to be Associate Administrator of NASA.
Well, so I studied astrophysics, and I was really inspired by some of these missions. Frankly, I remember when I was 8 years old, I got this book about the Voyager missions and some of these telescope that Nancy Grace Roman, right? I really started imagining. That was in the 70s when I got this book, and that inspired me out of the little mountain village in Switzerland to be where I am right now. I'm an astrophysicist, but I mostly focus my work about the sun and the inner solar system. So I know how to do mass spectrometers, and I've worked with teams. And what I fell in love with, Michelle, is really the ability of working with amazing teams. When I see a team, whether it's in athletics, or whether I see it in this control room right there, a team that is truly operating at their highest capability, I'm so excited to see it. It's the most beautiful thing, but it also gives me so much hope of all these other things we can do. So when I look at astrophysics, of course, I think of the classes and so many of the things that I learned in the late 90s that are no longer true. And that's what science is about, because we learn all the time. Can you imagine, even in 5 years from now, how classes everywhere around the world will be affected by this very amazing observatory that's being set up right now?
Yeah, there's going to be some very, very profound things. I mean, you were talking about looking at some of the first galaxies to form. And this, of course, is one of the reasons why we have an infrared telescope, which is different from Hubble, which was largely invisible light. Infrared actually allows us to see, to some extent, farther back in time, farther away in the universe, where the expansion of the universe has actually stretched out the light from visible light into the infrared wavelengths. And you mentioned this close relationship between black holes and galaxies. I mean, a lot of our viewers out there probably don't realize that we are orbiting around a giant black hole right now at about 500,000 miles an hour. The giant black hole in the middle of the center of the galaxy. And there seems to be some relationship between how galaxies form and how black holes form. But there's a real mystery about these big black holes that we see so far away and therefore so far back in time. Maybe give us a little more sense about, this is one of the things that as an astrophysicist, we look at and we say, I don't understand how that happened.
Right, it's truly a chicken and egg problem, right? Kind of right now, it seems to be the case that black holes and galaxies really coexist, right? It's actually really hard to find a galaxy in which there's no black hole there. It really seems that it's a really important part of the galactic evolution. But how does that start? Is the black hole first? What is the role of the black holes? From the beginning. You talked about the interconnectedness, Michelle. We're right now setting up a small telescope we launched a few weeks ago. IXPE, the Polarimetry Explorer, and hopefully next week we'll be able to give kind of first light of that kind of X-ray observation, kind of again providing new insights about some of these kind of more recent black holes, kind of really trying to understand what the mechanisms really are, and that in those black holes, but also the environment around it. For example, the roles of magnetic fields that are so critical in so many of these areas.
I know for me, one of the things is when you're looking at the universe, in the case of Hubble, we've been able to see black holes that are gigantic. They are millions of times the mass of the sun. And we're seeing them at a time when the universe was only, say, 500 million years old. And black holes, we tend to think of as being formed by stars that die. But, when you think about the universe being that young, how did such a huge black hole form that quickly? And as an astrophysicist myself that studies stars, one of the things that I'm hoping Webb will shed some light on is the fact that the very first stars in the universe might have been quite different than the stars today. And maybe that's something you can give us a little bit of an idea. Why would the first stars be that much different from the stars we see around us right now?
I think it's a really great question, and I think it's one of the most amazing parts of really talking about how we relate to our universe. And that is that, of course, when the universe starts at the beginning, the atoms that form really are much less rich in terms of diversity than we have today. On my hands, I have gold and platinum rings that my wife gave me. And we know that those are not from the beginning of the universe. Frankly, they come from neutron stars that are merging, that are much, much later, kind of after a lifetime of a star. So when you look at the first stars, like what you have, kind of the material you build with is much lighter than stars that are that most of the stars that we're looking at night through a telescope, because those stars are next generation stars in so many of the cases with much heavier components that are there. So the question really is, how do you build those first stars? And frankly, how do they then kick off that evolutionary process? There's a lot of models. And the data will, of course, constrain these models. That's what we call learning, right? It's say, this model is correct, this model is not correct. And by the way, there's an observation that none of the models predicts, which is the element of surprise. We can always bet on the element of surprise, Michelle. Frankly, often the surprising parts are the most important ones.
I sort of like that. We're talking about the history of chemical elements, but in there is always the element of surprise. Yes, the universe began with hydrogen and helium, a tiny little bit of a couple other elements. But as you mentioned, everything that really makes us up, the things that make up a human body, like carbon or the calcium in our teeth or phosphorus or sulfur, the things that we need for our DNA.
We have completed this move of the 3-door latch to safe. So we're going to proceed with the 2-door latch.
One of the things that we're really hoping that the James Webb Observatory will shed some light on is what the universe was like before most of that formed. I mean, really the origins of the stuff that we are coming from. But there's another part of our origins too. You mentioned, in 5 years' time.
Ready to begin the 2-door latch off stow. That is motor move 3 of 20. The command line looks good. You're go to execute.
Copy that. CC, go ahead and execute. Executing.
And you're go to continue.
Copy go. CC, how to go to continue.
One of the things that I'm really looking forward to is being able to maybe in a few years from now point to a star up in the sky and say that there's a planet around that star that has an environment similar to us here on Earth. Maybe to take us through how will Webb do that? How will Webb be able to explore what the actual environments on planets that far away around other stars? How will Webb be able to do that?
So if you go back in time of the Earth, of course, long before we were here, the atmosphere of our planet was very different. And frankly, the emergence of life on the atmosphere here, kind of in that Goldilocks zone, right, where water can cool, the emergence of life really changed the atmosphere. Frankly, there's a number of papers out there that said a large fraction of the nitrogen in our atmosphere may very well be from the emergence of life. There's other, of course, elements, oxygen type of ozone, elements like that really come, of course, are very much part of that cycle of life that is here. So as we look at other planetary atmospheres, right, the question really is, what are the patterns there? And can we find patterns that are indicative of the presence, both the ability to have life there, but even in some cases, kind of the follow-up or kind of the consistency with life there. Certainly from what we've learned here, but perhaps also other versions that we yet have to we have to learn. Of course, what's so hard about life is we have n equals 1. We know only one life. All life on Earth is related, and we learned a lot when we went from one solar system to many solar systems, stellar systems. Frankly, many of the models crumbled within weeks of the first observations that were published in 1995. So when we look at life, I'm sure similar things will happen. But for me, that's why that's so exciting, Michelle.
Well, that's absolutely wonderful. So once again, we're speaking to Dr. Thomas Zerbucket. He's the Associate Administrator for Science at NASA. Thomas and our audience out there, we're going to take a short break. We're going to take a pause in the commentary, and we will be coming back at 11 o'clock in the morning Eastern Standard Time to resume our commentary. But Thomas, thank you so much for joining us. What an exciting day, as you said, very emotional. And I'm just so pleased to be able to be here on the floor beneath you. So I'll wave to you from down in the building.
Yeah, that's true. I want to thank you for all the amazing work you've been doing, Michelle. It's just been wonderful. I've watched you many times from different locations. I know you have exactly the same passion I do about this amazing science, and you can't wait to get those data back in just a few months' time.
Absolutely. Thank you so much for joining us. We'll be back in our commentary in just a few minutes.
Thank you. Yeah.
Okay, and OC, that motor move completed successfully. We're ready to continue with 693.052. The door latch to safe, smooth 420.
Roger that. That is on the wing.
And that command line looks good. You're go to execute.
Copy. CC, go ahead and execute.
And you're go to continue.
Copy, go. CC, you have the go to continue.
And stand by while we review the parameters.
Okay, standing by.
And OC, the parameters look good. You're go to continue with the move.
Copy, go to continue. CC, you have the go.
Ready. And OC, the motor move is in progress. This will take about 14 minutes.
Copy, 14 minutes. Well, stand by.
the depth lead on ops with the status. We are on step 4 of 20 of latching. We're latching the 2-door to the safe position into it a couple of minutes now. Again, strains look really good, nice and low, and our strain offset is matched our predicts, so no updates required there.
Excellent, Mom. Copies. Thank you.
This is Ocean.
here at the Space Telescope Science Institute in Baltimore, Maryland. And what you're seeing on the screen above me is a live footage from the Mock Mission Operations Center for the James Webb Space Telescope. And then to my left is an observatory visualization tool which is showing you real-time data, telemetry, as they say, from the James Webb Space Telescope, which is now over 600,000 miles away from us, on its way out to an orbit about 1 million miles away, past the moon, L2, the Lagrange point. And just a few minutes ago, we successfully deployed the final part of the primary mirror, the side wing. So this has been a wonderful morning so far here in Baltimore. We still have a few hours to go as they latch this primary mirror segment in place.
status. We've just completed the two-door move to safe position. So now we're in a position to stop the deployment motor and reset.
Copy, copy.
See, this is definitely for depth lead, that measurement is considered successfully. We are going to continue into 673.054 to terminate SPX-256.
Copy that.
That command line looks good. You're going to execute.
Copy. CC, you have the go to execute.
You're going to terminate.
Copy, go to terminate. You have the go.
This is step up. You are going to disable SCFS ID 256, step 55. The command line looks good. You're going to execute.
Copy that. C, you have the go to execute.
Executing.
And you're going to disable.
Copy, go to disable.
Roger. RTCP is complete.
Copy.
Okay, and OC, you are going to execute the DEU stop deploy at 5-6. That command line looks good. You're going to execute.
Copy that. CC, you have the go to execute.
Executing.
And you're going to continue.
Copy, go to continue.
Roger. RTCP is complete.
Yeah, OC DevOps can confirm that the motor is stopped. We're ready for 693.057 DEU to standby. And the command line looks good. You're going to execute.
Copy that. CC, you have the go to execute.
Executing.
You're going to continue.
Copy, go to continue.
The DevOps can confirm standby round robin. OC, we're ready for step 693.058 to raise the integral gain.
Copy that. On the window.
And that proc looks good. You're going to execute.
Copy. CC, you have to go to execute.
Executing.
you're go to continue.
Copy, go to continue.
To recap some of the story of the James Webb Space Telescope, as well as talk to some of the expert scientists and engineers that are working on that. So if you're just joining us, you can also talk to us on social media. We ask that you use the hashtag #UnfoldTheUniverse. So hashtag #UnfoldTheUniverse, and we'll get to as many of those questions as possible. So this has really been a momentous day. Everybody is very happy with how things have proceeded. I think that it's a really nice chance to kind of go back and talk a bit about the larger story of how the James Webb Space Telescope got to where it is today, over 600,000 miles out in space, headed toward a Lagrange point, a balance between the sun and the Earth's gravity, where it will hopefully have many years ahead of it observing the early universe, exoplanets, and all things like that. So this telescope has actually been in development for many, many years. A lot of people say that 1995 was the time when it began, when we started planning for this observatory. And what you're seeing now is some footage of actually putting together the primary mirror. Much of this work, building the primary mirror and the observatory and testing it, was done at Goddard Space Flight Center. These are acoustic and vibration tests, which were necessary to make sure the telescope could withstand the pressures of launch. So there's our acoustic test chamber, and you can see there the telescope is wrapped to keep it clean. This is a vacuum test that was done at Johnson Space Center in Houston. This is what we call Chamber A. This is the largest vacuum chamber that NASA has, and this was made during the Apollo era. It was actually large enough to fit full command modules of the Apollo mission in there to test. So what you're seeing now on the screen in front of you right now is live footage from the MOC, the Mission Operations Center. That's right above me as I'm speaking to you. And to the left is our observatory visualization tool. This is a computer-generated image, but this is a live image generated by data that's actually coming from the telescope as we speak. So what happened just a few minutes ago was the starboard side of the primary mirror, the mirror wing, was released into place. And that's an incredible accomplishment. The mirror is now fully unfolded, and that's for all of us here.
This is time we're ready to continue with 693.059.
It's incredible relief and some incredible joy.
Command line looks good. You're going to execute.
Prior to that,
you'll see.
Go ahead and execute.
Executing.
You'll hear me pause as I listen to what's happening in the control room. They are just making sure that all the different launches are firing successfully.
Roger, go.
And as I mentioned, this procedure will go on for a couple more hours. We will stay with it through the entire thing so that at the end we'll be able to tell you that the mirror has been safely latched into its final position. And that will mark the end of some major commissioning efforts of the James Webb Space Telescope. There is more to come. This is not the last phase. After this, we will be focusing the primary mirror, which is made of 18 independent segments. And then there will begin commissioning of the science instruments as well. So I think right now it's also a chance to sort of talk about the journey that Webb has been on. This is a portable, clean room. The Webb telescope, of course, had to be kept under very, very clean circumstances. And that left California on a special ship that is actually designed to take a lot of these specialized spacecraft cargo to the launch site that the European Space Agency runs in Kourou, French Guiana. This is in South America. And here you're seeing footage of that portable clean room with the Webb Observatory inside being taken off the ship and being loaded onto the place where it will go up on an Ariane 5 rocket. So that's part of the journey of Webb. And here you see actually opening up that portable clean room. Webb is in its stowed configuration, folded up. This is one of the reasons it's been so exciting the last couple of days. This observatory, for the first time, we've launched an observatory that was so big, the mirror had to be folded up. And as people often compared it to origami, folding up the telescope, so it could fit inside the fairing of the Ariane 5 rocket.
Stand by.
Once again, let's go. We saw the final part of that major commissioning of unfolding the mirror happen.
And OC, you are going to continue to move the motor.
How's the copy? Sissy, how's the copy?
As they continue the latching procedure, one of the things we can also look back on is the launch. This was a Christmas present for all of us. This was about 7:30 in the morning Eastern Standard Time in the United States. And there you see the launch of the Ariane 5 rocket. It was an absolutely perfect launch. They were able to get enough energy from the launch itself to save some of the fuel on the Webb telescope, which we hope will extend its life. And here you see some of the people at Mission Control in French Guiana cheering after the successful launch. And what you're looking at here is an animation of the observatory going away from the rocket. This is not an animation. This one here is the actual footage. There was a camera on the rocket itself. And here we see the Webb telescope coming off the Ariane 5 second stage on its way out to the Lagrange point, L2. That's about 1 million miles away from Earth. It's on the other side of the moon. It's a wonderful environment for an infrared telescope that needs to be very cold. Here you're actually seeing, again, this is real footage from the camera. You're seeing the solar panels unfold. This was the very first of the actual unfoldings that had to occur because now the telescope was able to power itself up using radiation from the sun. And then after that, of course, came the amazing. Oh, there's everybody celebrating. People, of course, put in huge amounts of time. They were here over the holidays. All of us have been working straight through Christmas and New Year's, of course. It's been wonderfully joyful, but there are a lot of families back at home that I'm sure missed us as well. Here's an animation of some of the major commissioning points that we've actually accomplished. So the solar array was unfurled, and also the antenna that allows the Webb to communicate with the Earth. Now you see the Webb moving up from the sun shield, which is now beginning to unfold. This is a 5-layer Kapton sun shield. It's a material that's very much like mylar. It's a very thin, very strong material. In this case, it actually has some silicon in it to make it more reflective, and also put together in small segments so that it's very strong and can withstand any sort of small impacts from micrometeorites, which we do expect over the course of the mission. And now that incredible sun shield is fully extended. The secondary mirror came out a few days ago. Yesterday, we saw the first of the wings of the mirror, and today we're just completing the second. So now that we've gone through a little bit of an update as to what the tremendous journey that this observatory has been on, it's my pleasure to talk to Lee Feinberg, who is one of the senior engineers on the Webb telescope. And he's going to talk to us a bit more about some of these mirrors and some of the technology in Webb. So for one thing, Lee, wonderful to see you. We're all isolated from each other so that we can speak without masks. I'm downstairs.
He stopped at the spot he wanted to stop at.
Hi, Michelle.
And we are ready to continue to begin the 3-door cup latch to capture move.
So as we said,
okay, and that is move 520. The command line looks good. You are good at execute.
So in our conversation, you'll probably hear me pause just when you see that there are just something skating. Lee, were you sitting?
I'm sorry, can you say that again, Michelle?
Where you're sitting, can you hear those calls from the mic?
I can hear them, yes.
Okay, right, excellent. So for one thing, but before we launch right into the technical, tell me a bit about how you're feeling right now. We're human beings first.
Yeah, well, I feel good. I feel like the mechanical and the deployment teams really have done a phenomenal job. The optical team actually is just about to get started, so it's sort of a transition time. But to see a full primary mirror, this is something we've really been thinking about for a long time, and it's just a great thing to see and to be ready to start aligning those mirrors.
Absolutely. Well, let's talk a bit about those mirrors. I mean, that's sort of the expertise that you bring with us. So to begin with, these are very different mirrors than most people are used to in their regular life, in many, many ways, obviously incredibly specialized. Tell us about some of the ways these mirrors are just completely unique and very different.
Yeah, well, let me start by just saying, when we started this a couple decades ago, we knew from the very beginning that one of the hardest parts of making the observatory was going to be the mirrors. And in fact, if you go all the way back to the first project manager, Bernie Siri, he used to have this chart that would show that, one of the key goals was to make a mirror that could be lighter than the Hubble mirror by about 10 times per unit area. And it had to work at incredibly cold temperatures, minus 400 degrees Fahrenheit. And it had to have a quality of the mirror that was approaching the quality of like visible mirrors, like the Hubble Space Telescope kind of image quality. And so these were, a set of challenges that were extremely difficult. There were some people who thought we couldn't even make mirrors that were this light and this quality. So actually it was a pretty collaborative effort. We actually worked with other government agencies, including the Department of Defense. It was a collaboration to invest in multiple different mirror technologies. One of which was actually a technology in which the mirror has a bed of nails under it, a whole series of little tiny actuators. But one of them was a beryllium. And the beryllium that was developed for Webb, it was actually a new form of beryllium. They called it an optical grade beryllium. And it was developed by a company that was called Brush-Wellman that then later became Materion. But this optical grade beryllium was supposed to be more uniform and was going to have better properties for being a telescope. And the key, though, was could you build large mirrors that are about almost 1.3, 1.4 meters in diameter? These are segments that are incredibly lightweight. So you have to be able to machine the mirrors from the back to lightweight them. And so it was a several-year technology development. It really took groups from all over the United States. The machining was done in Alabama, and the polishing was done in California. And here actually you could see some of the beryllium billets that were made in Ohio. So we developed the technology, and there was a mirror that was almost the full size of what the ultimate segments look like. We called it a prototype mirror. And here you could see the light weighting of the mirror from the back. And so that was the first phase, was just making a single mirror that could meet our requirements, including a gold coating that would reflect the infrared light. And so it was a large team effort. Ball Aerospace in Boulder, Colorado kind of led that team. And that mirror actually was competing with other mirrors. We had a very intense process by which we selected which mirror technology we would use. But beryllium won out because of its superior qualities at these very cold temperatures. And that's really the key. Beryllium has this amazing property that when you take it to these very cold temperatures, it's incredibly stable. There's a material property called coefficient of thermal expansion. And for beryllium, that material property is like as perfect as could be at these very cold temperatures. And that really was one of the key reasons we selected beryllium, along with the fact, one of the big benefits is it's extremely light. And if you look at how large the telescope is, 6.5 meter diameter, if we didn't make mirrors this light, we would not be able to lift them with a rocket. So it was a long effort. We then had to manufacture the mirrors, but that's what led to the mirrors.
The story actually goes, even farther back than that. So where was the beryllium mined? You're saying that this is sort of a new type of beryllium, but where did it start? Where did the beryllium actually come out of the ground?
Well, so it's actually mined in Utah, and it's mined in sort of these chunks and rocks that eventually will get ground up and eventually made into a powder form. And that was one of the things that they were able to do, was make a finer powder, a powder that has more spherical qualities. And then once you get that powder, and this was what Brush-Wellman did in Ohio, just outside of Cleveland. Once you get that powder, you can actually do a process that's called hipping. It's hot isostatic pressure. It's a process that puts heat and pressure on the beryllium and forms a billet of beryllium, a block of beryllium, that we would slice like an Oreo cookie into two mirror blanks. And that's how we got sort of the large blanks that would make up what we would ultimately then machine. And so the first step was to go from Utah to Ohio, and then they would be sent to the Cullman, Alabama, where the machine shop was, that would lightweight the mirror. And they would also put on the front surface, they would literally machine a surface that was approximately the surface we needed for each mirror. But that was only the beginning, because the next phase was you had to grind and polish the mirror. And that typically when you make a mirror, it's the polishing that's the hardest part. And actually the hardest part of that process is testing the mirror. And one of the key things we had to figure out was, how do you test mirrors that are inside of a cryogenic chamber to the level that we needed? And nobody had done that before. And we also needed to make sure that all 18 mirrors matched each other, so that if you made one mirror and then you made a second mirror, and you align them relative to each other, they need to have the same curvature. And that actually turned out to be one of the more difficult problems. So we had to develop methods, for testing mirrors and then for polishing the mirrors. When you cool a mirror down to minus 400 degrees Fahrenheit, it will literally deform because things shrink, but they shrink in a way that's not perfect. And so when we made these mirrors, what we did is we would put them inside of a chamber that would cool them down. We would test them with devices that are outside of the chamber. And once we knew how they deform, we would warm the mirror back up, send it back to the place that polished the mirror, and we would polish the inverse of the way they deformed. That process we call cryopolishing. And here you can actually see the mirrors going into the chamber. This is actually at the Marshall Space Flight Center. It's a chamber that was used for the Chandra Space Telescope, was converted for testing these mirrors. We put a special liquid helium shroud inside of it. And we also developed new test equipment that could work in the presence of all the vibration that we would get inside of a vacuum chamber. So we did all that work. We polished the mirrors with the inverse to deal with these cool down effects. And we also had to deal with the fact that these very lightweight mirrors deform under gravity. Right now is actually the first time these mirrors have ever been in microgravity, but on the ground there was always gravity, and literally the mirrors are so light that the gravity would deform the mirror. So we not only had to polish them for the cool down, but we also had to polish them for the effects of gravity and deal with the effects of gravity. And so we had to combine all that with the fact that we had 18 mirrors that all had to match each other. So it was a challenging process. The whole effort from technology development to manufacturing was about a decade, from about 2000 to 2010.
It's absolutely incredible. And what you just said, the whole idea is you get these 18 mirrors, and they all have to work together as one single mirror. And that's a big part of the commissioning that's actually going to be happening in a couple in the future now. But let's talk about some of those. There's actuators on the back, right, that can control each of these mirror segments individually.
Yeah, it's funny because a lot of people see pictures of the Webb Space Telescope and they see the front, and it's gold and it looks amazing. But for an engineer, it's really the back of the mirror that is where all the engineering goes in. And in fact, maybe if we could freeze the picture in about a second, if you look at the back of the mirror, that's where all the engineering is. The first part was the light weighting and the rib structure and how you do that so that the mirror is strong enough to launch. But then you also have to be able to connect actuators to the mirror. And each primary mirror segment actually has 7 different actuators. There's 3 pairs of actuators that you can see in this video that are, we call them bipods, that literally allow the mirror to tip and tilt and move around in 6 different degrees of freedom. And then we have also one actuator at the center of the mirror, which allows us to change the curvature of the mirror. And so each of the primary mirror segments actually has 7 actuators. And it wasn't obvious exactly how to design those from the beginning. In fact, the very first design only had 3 actuators plus a central actuator, so 4 total. And as time went on, we understood better, how we needed to move the mirrors in order to make a perfect primary mirror over the full primary. And we also needed to understand how to mount those actuators. The actuators themselves are actually, an amazing achievement themselves. They were designed by Ball Aerospace using these special little gear motors that can move the mirrors in steps that are so small they're just a fraction of a human hair. In fact, the smallest step that we can move is about 1/20,000th of a human hair, and that is so that we can move the mirrors into position so that all 18 mirrors together will be aligned to less than a wavelength of light if you were to kind of go across the whole surface. And so we needed an actuator that could move in these tiny steps, but do it at minus 400 degrees Fahrenheit. And that's a lot of complexity and challenges. And then at the same time, these actuators have to survive launch. And they, so they have to be able to deal with, vibrations, large vibrations, and get the mirrors into the right position initially. Because when we launch the mirrors, we actually have them in a special position that is designed for launching them, where the mirrors are up against, we call it a hard stop, so they're in a nice, secure position. But actually, in the coming week, we're going to deploy the mirrors about a half-inch forward, each of the 18 mirrors, to this point where we can start aligning them. So these motors had to be able to get you forward by about a half an inch and then move in these very small steps. And so there's a lot of different challenges. It took a huge team of people across the country. There's companies that develop the motors in Florida, a company that developed the bearings in New Hampshire. I mean, all over, while Webb is an international collaboration, the telescope itself was actually built within the United States, but maybe 20 or 30 states made major contributions just to the primary mirror itself. That's how significant an effort it was, and that's how much coordination it took. The team from Northrop Grumman, the team from Ball Aerospace, the teams from L3 Harris and ATK that all worked on this primary mirror. They had to work with all these subcontractors from all over the United States to make all these pieces.
In fact, I actually believe we have a map that we could show the different collaborators, all over the United States on the primary mirror. I think they're gonna run that. Yes, here we are.
Okay. Yeah. I mean, it's literally all over the country, and obviously the people who kind of worked on this got a lot of frequent flyer mileage. But yeah, I mean, it was a team effort. I mean, we had 3 different NASA centers early in the program working on this. I come from Goddard, which was the lead for the observatory and the telescope, and where it was all integrated. But we had the folks from Marshall Space Flight Center who had a lot of, who helped us with the testing and the mirror technology. We had JPL involved in the algorithms. And then there was this large contractor team led by Northrop Grumman, but with companies all over the country. And for the mirrors, it really was Ball Aerospace that was the lead. So it really took a large collaborative effort. And one of the really neat things about it was when you work on something like the James Webb Space Telescope that is so incredible in its capabilities, it's not hard to get people to want to work on it. You get the most incredible people, and they're so dedicated because they know how exciting it is. And so, and they all, everyone worked really collaboratively. I know a lot of the folks who worked on this, from the people who were, ground the mirrors, people who put the motors together, I know they're all following. A lot of them send us messages. A lot of them haven't even been on the program for over 10 years, but they're following every little step in detail with a lot of pride. And I will tell you that you see a few folks on television that you're watching in the Mission Operations Center, but for every one of those people, there's probably, hundreds of people who led up to that point who are all watching with pride. And that's what it took to get to this point.
Yeah, it's amazing. I mean, you talk about every step of the way. I remember at one point they were flying parts of the primary mirror for testing on the C-5, which is a gigantic aircraft that has this huge hollow interior that you can take very, very large objects. And I got a chance to talk to the flight crew, and these young men who were actually in charge of flying the airplane were so excited to be flying the James Webb Space Telescope. They just thought that was a wonderful thing to do. So we talked a bit about about building and testing the primary mirrors, and then the idea that these segments, like you said, they have to function in zero gravity, which is something that you can't do on Earth. You need to make sure you compensate for that, and also at the low temperature. But what comes next in commissioning is something pretty incredible, and that is getting all of these 18 segments to work together. And maybe you can step us through a little bit about what comes next, with a little bit of a timeline and what we're going to do to actually make this thing into one big mirror.
Yeah, well, so first of all, in just a few days, we're going to start exercising all the little motors. There's actually 132, we call them actuators, total on the telescope. There's 7 on each of the primary mirror segments, and there's 6 on the secondary mirror. And so the first thing we're going to do is what we call mirror deployment. That's that's about a week and a half to 2 week operation. So that'll be starting actually as early as this Tuesday. And that's just to get the mirrors at a point where we can start tipping and tilting them in order to align them. But after that, we'll wait a little bit. We wait about a week, or a little over a week, for the instruments to get cold enough so that we can get images. So we can't actually we can't get first light until the instruments are cold enough. This is one of the things about being an infrared observatory, is you need very cold detectors. So we got to wait for the instruments to get cold. But once that happens, the very first thing we're going to do is we'll look at a bright star, a bright isolated star, and we expect to see 18 separate images of that star that are really blurry. Okay, and it's not going to look real pretty. And
actually, we have the animation. I bet we could run that animation again.
Okay, yeah, let's show that.
Yeah, that's right.
Yeah. So you can see light will come into the 18 mirrors, and they'll behave like 18 separate telescopes because they're not aligned yet. So each mirror actually forms a telescope between the primary mirror segment and the secondary mirror, and that makes a series of spots. And one of the first things we're going to do is find all 18 segments with those spots. And then ultimately what we need to do is get those spots on top of each other. So we'll align the spots, we'll align those primary mirror segments well enough that we have nice spots that we can form on top of each other. We call that the forming on top of each other image stacking. But it is a little bit of a long process because we have to take images, we have to figure out how to move the mirrors. We actually have a special wavefront room here at Space Telescope Science Institute, and we'll have a team of real experts from Ball Aerospace and from Space Telescope Science Institute and from Goddard that all will work together, and they'll get the images, they'll analyze them using software that they've rehearsed all of this with. They've done simulations of all of this, and we've tested a lot of this with a testbed telescope that was built up, and they will go through and they'll get those 18 images on top of each other. And at that point, we're ready to get into what we call phasing. And phasing is a little bit like, if you think of sort of if you think of waves in an ocean, imagine you have different surfers and they're each surfing on a different wave. What we need is for all of those surfers to be on the same wave. And so we need all of those mirrors to be essentially on the same wave of light. Light travels in electromagnetic waves, and we need them all to be on the same wave of light. Otherwise, we will get images that are kind of confusing. And so we'll go through a process. First, we go through a process called coarse phasing, where we'll get all the waves, all the mirrors lined up to maybe 1 or 2 waves. So imagine the surfers are almost all on the same wave, but not quite. And then we'll go through fine phasing. And fine phasing is the very final sequence. We actually use special algorithms that were developed primarily, actually, if you go all the way back to when Hubble Space Telescope had its blurry problem, the spherical aberration problem. There were algorithms that were developed to figure out the prescription of Hubble so that we could repair Hubble. And those same algorithms are actually being applied here to align the primary mirror in this very final stage. It's almost like you have a blurry primary mirror. And so we'll take images in the main science camera, the near infrared camera, but we'll take them through focus. We'll take different, it's almost like you move the focus on your camera. So we'll take a series of images and then we'll run them through these special algorithms that we've developed. We started with what we did on Hubble, and we've adapted them for the fact that this is a segmented telescope, but that's what's going to allow us to align this mirror perfectly. And eventually we're going to get an image of a single star. So a star will come in very early on, and maybe, a couple weeks, 3 weeks or so, it'll look like 18 separate images. But we think by sometime in March, we'll actually have a star form a single image. And that's kind of the first goal of the alignment process. And then from there, really what we're doing is we're aligning the secondary mirror to give us an image of a star that works in all the 4 instruments, over the full field. That takes about another month and a month and a half. So the whole process is about 3.5 months. We call it wavefront sensing and control. But really what it is it's aligning all these mirrors to act like a perfect telescope. And at the end of all that, we'll be able to hand off the telescope to the science instrument teams who will be finishing up their calibration, and then get on with some of the early science.
Well, that's absolutely incredible, and that's probably a nice place for us to break, because we're going to bring on one of those scientists that is waiting to use Webb. So again, we're talking to Lee Feinberg, one of the senior engineers on the James Webb Space Telescope. Such a pleasure to have you here, Lee. Congratulations.
Thank you, Michelle.
And I hope the rest of the day goes very well for you.
Yep. Thank you very much.
So for those of you that are joining us, you're watching live coverage of the commissioning of the James Webb Space Telescope. We are all here at the Space Telescope Science Institute in Baltimore, Maryland. And I'm Michelle Fowler. I'm from Goddard Space Flight Center. And if you'd like to join us later on, we'll probably have some time for social media questions. So you can use the hashtag #UnfoldTheUniverse. So once again, hashtag #UnfoldTheUniverse. And that will allow us to see your questions and answer some of them on air. So the next person that I'm going to talk to is Dr. Antonella Nota. And Antonella works here at the Space Telescope Science Institute. She's the representative for the European Space Agency. So Antonella, first off, many congratulations. It's been a wonderful morning so far. How are you doing?
It is amazing. It has been an amazing morning. And the team made it look so easy. We know how many years of preparation there were behind the moves this morning, but it just looks so amazingly easy. I'm so delighted to represent the European Space Agency at this time. And this is the moment we have been waiting for so long. So we are ready to move to the next step.
It's incredible. So for those of you that may have just joined us today, we deployed the second and final wing to the primary mirror. And that was a major commissioning exercise. There are definitely things to come, but this is, what's been accomplished is absolutely historic and really incredible. You're looking at live coverage from the MOC, the Mission Operations Center. And occasionally you'll hear me pause because we're listening to the commands, so that's all fine. And in between commands, we'll have a chance to talk to Antonella. So, Antonella, you are an astrophysicist, an astronomer, and tell us a bit about some of the major science goals that you're looking forward to. But maybe before we do that, we should back up a little bit and talk about infrared. Why is Webb an infrared telescope, and why is that so important?
It is infrared because it's the sources that Webb wants to look at emit in the air. For example, when we look at the distant universe, we're all familiar with the Hubble Deep Field that Hubble took several years ago. And we know those distant galaxies, born 400 million years after the Big Bang, just at the very beginning. Hubble, with a 2.4 meter, could push us to see that horizon. Webb will go way past and look at the first few million years and see those galaxies that are small, irregular, compact. We want to know how those galaxies became the Milky Way of today. And those galaxies emit in the infrared. Here you see a beautiful fly through the Hubble Deep Field, and it's amazing that in the size of a pencil, we could see thousands and thousands of galaxies, including some very, very old, as I said, as old as 400 million years after the Big Bang. So we're talking 13.2 billion years old. And those galaxies look very different from today. And so I think the challenge for the astronomers is to understand how they evolved from how we look at them then and how we see them today. And Webb will do that. Webb will also be able to actually individually take spectra of these galaxies, because it has powerful spectrograph on board, including, for example, NIRSPEC, the workhorse spectrograph provided by the European Space Agency. And NIRSPEC will be able to actually take spectra. And for all of you who are watching, spectra are when the light of an astronomical target gets split into its component. Like, for example, rain droplets do after a thunderstorm, and you see a rainbow. So why spectra are important? Because spectra tell astronomers what the object is made of. Images tell us how objects look like, but we really want to know the physical, chemical composition, the elements that are there. And for that, we need spectra. And because Webb will be so powerful, 100 times more powerful than Webb, we do believe that we'll be able to take spectra of all these faint objects that we see at the edge of our observable universe.
We are ready to continue with the review.
It's absolutely incredible. For those of you that might not be familiar with the Hubble Deep Field, which was the image that we had started with there, when Antonella says the size of a pencil, it's looking down the narrow hard pencil, that tiny little bit of the sky. Anywhere you look in the sky, there are many thousands of galaxies very, very far away from us. So again, and for our viewers, we often get a lot of questions about how is it that we're able to look back in time. A lot of people, I've actually gotten questions on social media recently about what direction do you need to look to see that far back in time. Maybe you could give us just a little bit of an astronomy lesson about how is it that we can view the early universe?
Yes, you look anywhere, because wherever you look, your eyesight basically looks as far as you can go, and the farthest you go, the farthest you go back in time. So as I was saying, these very faint galaxies that we see in the Hubble Deep Field have traveled for the light for those galaxies has traveled for 13.2 billion years. So we see them today as they were 13 billion years ago. And this is the powerful of this amazing telescope. We can actually look at the beginning of the formation of the universe, because one of the things that Webb will do, it will be focusing on origins. What is the origin of our universe, as well as other origin things like how stars form, what's the origin of stars. So you can see the Webb is going to look, we hope, up to the first 100 or 200 million years after the Big Bang. If we're really lucky, we might even see the first star. Thomas was talking about first star earlier on. That's a challenge, but this is one maybe of the surprises that the Webb will bring us, together with many others, I'm sure.
I've also gotten questions about who gets to use Webb. How is it, one of the questions that I actually got on social media is, do only people from NASA get to use Webb? And that's very much not the case. You work at the Space Telescope Science Institute, where a lot of this happens. Give us a sense. How is time on Webb allocated?
Absolutely. So the entire worldwide community can use Webb to observe. They just need to have a good idea and a laptop and an internet connection, and they can submit their proposal. And their proposal, they will say, I want to use these instruments to make this amazing discovery, will be evaluated by a group of peers, experts in the various fields. And if that idea is compelling, that idea will be scheduled on the telescope. And as we speak, we have already a first year already scheduled of observations that have been given out to the community, to the instrument builders who have the right to get the fruit of their hard work over so many years, and the early release scientists who are actually...
And OC, Dep Lead's ready to begin with the 3-door latch to 200, move 9 of 20. And
yeah, there is a group of scientists
to execute.
Right or that, this you have to go to execute.
And you're going to continue.
Hope you go to continue.
This is so exciting to hear this and to hear, what's going on in the vault at the same time, which is one floor below. And kudos to the team for doing such an amazing work. For astronomers, this is the biggest gift that we can get, and we're just looking forward to see what will bring us. But I was saying, the early release science, this is something that the director of STSCI used some of his precious directory discretionary hours to actually tell the community, submit proposals for approximately a couple of 100 hours, and they will be evaluated with this caveat. They will be done right away. The observation will become public. They will go in the archive. They will be made available to all, because this observation will show the capability of this very powerful observatory. So there are a number of programs, some of which Europeans, that are going to execute in the very, very first few months. And those are the ones that will show the world, how actually web performs. Before that, we will have the early release observations. And those are really the ones that I'm waiting for to see. This is super secret list of targets. I don't know, what targets will be. But I know one thing, that they will be absolutely spectacular. And they will be shown to the world 200 days after launch, at the end of the instrument commissioning. But I hold your breath, because they will be just phenomenal.
So we've talked a bit about the early universe, and I know that another, primary science goal of Webb has to do with exoplanets. We mentioned that a little bit with Thomas, but I think maybe you could take us a bit more through how does Webb actually analyze the atmospheres of planets around other stars?
Absolutely. So this is a technique that Hubble had already pioneered, and I want just to tell the community who is listening. When Hubble was launched, we didn't know exoplanets. Now we know that every star has exoplanet around. So this technique allows to study the atmosphere of the exoplanet as they move in front of their host stars. And by doing that, we can see via spectroscopy what actually the components of that atmosphere. And so you can see here the planet basically moving in front of the star, the light dipped, and in the infrared we can see important component elements that are the building block, we believe, of life in the future. So water vapor, carbon dioxide, oxygen, all the complex molecules based on oxygen. Why we're looking for these molecules? Because the ultimate goal is to see if there is life out there. So we start looking at the building blocks. And Hubble has already moved the field forward, but it's a small telescope. We do believe that being 100 times more sensitive, Webb will just revolutionize this field. So our knowledge of exoplanet composition will be just spectacular. And maybe we will find another Earth out there. That's the big, award for this work.
Stand by for review.
Absolutely wonderful. Antonella, thank you so much for joining us. I hope the day continues to be joyful and exciting, and after this we all get a bit of a break. So thank you again for joining us. That's Dr. Antonella Nota, the European Space Agency representative here at the Space Telescope Science Institute. Thank you so much.
Thank you, Michelle. Good luck to all.
Thank you.
Okay, those parameters are good. You're going to continue with the motor move.
So the next person we're going to be talking to is Joe Spofera, and he will tell us a little bit more about some of the engineering aspects of the Webb telescope. For those of you that are just joining us, you're looking at live commissioning of the James Webb Space Telescope. I'm here at the Space Telescope Science Institute in Baltimore, Maryland. I'm Michelle Thaller. And Joe, thank you so much for joining us today. So to begin with, please introduce yourself and tell us a bit about your role on the Webb telescope.
So you mentioned my name's Joe Spofera. So been working on the Webb telescope for 16 and a half years now with Northrop Grumman. Currently the program dynamics lead for Northrop, as well as doing a lot of lead responsibilities for deployments with the team that we have, both what we've done on the ground and what we're doing today here at the Mach for on orbit.
And how's the morning gone for you? Are you as excited as everybody else and happy that things have gone well?
Yeah, it's been going fantastic. It really has for the last 2 weeks as well. Kind of everything we could have hoped for with all the operations have really gone quite nominal and quite to our expectations. So it's been a great commissioning so far.
So I guess one of the things that we have that we can show our audience are some footage from the tests that came before the launch of the James Webb Space Telescope, different tests in the clean room. So I believe we're going to roll some video, and you can tell me what we're seeing here, please, Joe?
Yeah, so this is actually the wing we're deploying today. So that was the ground deployment test for that wing the last time through. And actually, if we end up deploying both when deployed, this was our pre-observatory environment deployment. It was the last time that both wings were deployed at the same time on the ground. So you can kind of see the operations that went through there with all of the individuals in the high bay performing their jobs, getting through. So Down on the left there, watching that wing deployment, that's Paul Reynolds, who's downstairs right now as the dep lead doing the deployment, kind of watching for what's going on, both like he would have on the floor there, doing observing the deployment, looking to see any interactions, seeing what's happening. And he's down there right now today with the rest of the mock team, doing that deployment, watching for the telemetry to make sure we see what we want to see during the operation.
And actually, in this footage, you can see that there's sort of this black border on the outside of the mirror, and that's for a very specific purpose. Maybe you could tell us a bit about that.
If you're speaking about the black border on the very outsides of all the mirrors,
yes, that's right. Yeah,
that's there for the frill section that goes around the outside, the fixed frill outside of the mirrors themselves for thermal purposes, so that you kind of have this deep black right next to the mirrors that would not pick up the reflections that the mirrors actually.
And then, of course, that beautiful gold coating, and that's something that we get a lot of questions about as to why the mirrors are coated with gold. Give us an explanation for that, please.
I'm probably not the best person to give you the explanation for that one, but that is the best material that was determined by a number of scientists and engineers to give us the best performance for the optics and for taking data.
When you see the deployment and the tests that were done, the thing that amazes me is that all this was done here on Earth. There was no way to take this up into space and test it in space. And of course, in space, you don't have the influence of gravity, whereas here on Earth, you do. How do you design a test that you know that it's going to work in zero gravity? How do you design to take that into account when you're testing here on Earth?
Right, so the key thing there is we have to have a very good understanding of the loads that we want to see in the deployment and the loads that we want to kind of counteract or counterbalance in the gravity field. So we do want to try to maintain the resistances that we're trying to characterize or understand. So there are certain harnessing or insulation that provides a drag or resistance to the deployment. We still want to capture that in the test so we can characterize it and understand it on the ground. But you do need to counteract the gravity. You need to take away the fact that there's weight reacting on hinges and different locations in the deployable hardware. So there is an offload system that we use for that, and it was visible a little bit in the video that you did show, and I don't know if we'll be going back to that or not, but in the case of the wings, there was an overhead system, and actually you can see it right here. So there's a cable going up from the wing itself, from some hardware attached on the back so that we can attach basically through the CG of the wing. And you can see the cable running up to the crane structure to what looks sort of like a balance beam or a teeter-totter that's up there. And that cable, the beam that's up there can pivot and rotate, and the rotation point's aligned to the rotation axis of the wing so that you get a one-to-one rotation there. As the wing is turning, it's turning the hardware up above in the crane area. And at the opposite end of that rotating arm is also a weight to kind of balance that out, so you get a load or a tension in that cable that's effectively equivalent to what the wing weighs. So that now as you're rotating, the hinges that you have in this system don't actually see the weight of the wing. They're nearly weightless, as best as we can on the ground, so that you can instead try to capture just the loads of the nominal flight deployment, which would be, like I mentioned, something like a harness or some insulation, or some very low nominal drag that you get from driving at the one hinge as you rotate.
Absolutely wonderful. So it's been such a pleasure having you here, Joe. Congratulations again on everything that's happened this morning, and the continued commissioning of the telescope is coming up. So we'll let you go. Thank you so much for taking us through some of this testing.
Thank you very much.
Good to have you here. So for those people in the audience that are just joining us, you're looking at live commissioning of the James Webb Space Telescope. Today we have successfully deployed the second wing of the primary mirror. We now have the whole primary mirror together, and we are currently involved in latching that into its final place. So that procedure will be happening for a couple more hours, and we'll be here to the end of it. Right now, however, we will probably take a short break in our commentary, and when we come back, we will talk to some more experts on the James Webb Space Telescope. You'll be seeing more live coverage from the MOC, the Mission Operations Center, here at the Space Telescope Science Institute in Baltimore, Maryland. And I'll be here to take more of your questions on social media. Once again, you can use the hashtag #UnfoldTheUniverse, and we'll get to some questions after the break. So thank you very much, and we'll see you soon.
Então é isso aí, galera. Já damos aqui por concluído todo o trabalho de abertura da segunda parte do painel do espelho primário do James Webb.
Okay, and OC definitely just confirmed that those latches are good. We're ready to continue with the 3-door latch full.
Bom, espero que vocês tenham gostado. Vocês que estiveram conosco até agora, meu muito obrigado. Vou tirar o fone aqui. Ok. Então, é isso. Segunda parte do espelho primário já posicionado. Agora os ajustes finais, né? Ajustar os espelhos, os sensores, enfim, calibrar tudo para que eles possam obter futuramente todas as imagens. Bom, daqui para frente, como a gente vê, agora ele continua sua viagem, né? Até o L2 e até então tudo ocorrendo perfeitamente bem, tá? A gente agradece a todos que permaneceram conosco até agora. Para você que não é inscrito e que chegou agora no canal, seja bem-vindo, bem-vindo ou bem-vinda ao canal. Se você gosta de conteúdos relacionados à astronáutica, ciência, astronomia, tecnologia, enfim, assuntos relacionados a esse tema, se inscreva no canal. Aproveite e compartilhe com os amigos, com as amigas, e informe a todos. Bom, eu que agradeço a você, Samara, por você estar aqui conosco. Você é peça fundamental da nossa realização aqui, tá? Obrigado por todo o seu apoio, seu e de tantos outros inscritos aqui no canal que sempre vêm nos prestigiar com a sua presença, brilhante presença, tá? E logo mais, acredito que a partir das 18 horas estaremos no ar novamente. Ainda estou para confirmar a hora. Desculpa. Olha o Bolinha dando as crises dele existencial. Ele sempre tem que dar o show dele, não tem jeito. Daqui a pouco eu vou lá pegar ele para mostrar a vocês, mas não dá não. Ele tá muito arredio. Tá lá chorando, querendo ir pra rua. Não pode deixar. Ele acabou com a live. Mas tá bom, deixa estar. Tem grilo não. Faz parte, eu gosto. Tem só pra você ter uma ideia, são quanto? 10 gatos aqui em casa, 10. Tudo de vários tamanhos, espécies, cor, raça, tem de todo tipo aqui. Mas aí, galera, então é o seguinte, obrigado pela presença de vocês, obrigado também ao apoio cultural da internet, a maior e a melhor rede de fibra ótica da região, atendendo ao sul do Espírito Santo, norte e noroeste fluminense, região dos lagos, também na Baixada Fluminense, chegando ao Grande Rio e também agora abrangendo as áreas próximas à região do sul de Minas. Acesse o site www.itanet.com.br, confira lá os combos, as facilidades que a internet tem de oferecer e tenha certeza que a internet não é só um provedor de internet com preço justo que cabe no seu bolso, mas também um provedor de cultura, esporte, lazer, entretenimento, enfim, integração social. Grande beijo, Samara. Grande abraço a você do tamanho que nos separa, a todos que estão aí nos assistindo, que vão nos assistir depois. Não se esqueça, deixe o seu like, compartilhe, isso ajuda, fortalece o canal a crescer. Muito obrigado mesmo de coração e até a próxima, se assim Deus nos permitir, diante da fé de cada um. Samara, eu tenho que prender, eu já tinha me despedido, mas eu vou falar rapidinho. Eu tenho que prender, porque infelizmente nós temos pessoas aqui que alguns vizinhos que não gostam de animal, principalmente felinos, e costumam dar veneno. E aí a gente acaba tendo aquelas surpresas mais do que desagradáveis, né? Porque a gente acaba perdendo os nossos bichinhos de estimação por conta de pessoas insensatas, né? Pessoas que realmente não têm não tem compaixão. Você não tem compaixão com si mesmo, vai ter compaixão com os animais, é complicado. Não vamos entrar no mérito da questão. Cada um tem sua forma de pensar, né? Sua forma de agir, mas cada um tem que ser responsável pelos seus próprios atos. Então, muito bem. Então, tá aí feitas as minhas considerações. Lembrando, só mais uma coisa, já havia encerrado. Lembrando que nós estivemos fora do ar devido a problemas técnicos. O computador principal está sem a sua fonte, né, de trabalho, então por isso não posso utilizá-lo. E então eu estou usando uma outra máquina com potência menor, né, configuração mais fraca, para atender pelo menos a demanda dos nossos conteúdos aqui no canal, para que vocês não fiquem sem essa cara feia estampada na sua tela e sem também as informações de grande relevância, que é o mais importante, nossa figura aqui estranha. Bom, mais uma vez, muito obrigado à internet, obrigado à Inusitec, obrigado a você que nos assiste e fiquem todos com Deus na fé de cada um e até a próxima, se assim Deus nos permitir. Tchau, tchau. Tchau, Samara.